Okay, we are now going to be looking at seismic waves and measuring earthquakes. All right, so as we talked about, a seismic wave are the vibrations that happen after the rock breaks. Just like if you were to snap that ruler, it would vibrate and wiggle on both sides of that break or fault. So there are different types of seismic waves. There are in the body wave, which travels through the interior of the earth. There are P waves and S waves. So the P waves are the compression waves. So we call those the push and pull waves. So, and they're also the first waves you feel. So they're the primary. So it's P for primary and P for push and pull waves. So they compress. So you can see in this picture here, they get squished and stretched, squished and stretched. There are the S waves. That's S for secondary and S for shear waves. But they only pass through solid rock, so they won't go through any kind of mantle material or liquid. And they move like this. Then you have the surface waves that travel along the surface. And this is what causes most of the damage in earthquakes. They have larger ground displacements than body waves. And so we have the love waves with kind of like a shear wave, but back and forth instead of a rolling motion. This is more like if you were in an ocean and those waves or like a wave pool, how you can stay in one spot and it kind of goes up and down. That's what the S wave would feel like. The L waves are really more shaking you back and forth, so much more violent, if you will. And then you have the Rayleigh waves, which are, I guess, kind of more like that ocean feeling too. It kind of goes in a circle right here. We measure earthquakes using a seismograph. And so it's a lot really fancier now, but like the old school ones, and we still use the same concept. It's just a little more digital. It's a pin hung on a string or a spring, and it can write on this paper that's rotating around. And when the earth shakes, then the pin, because it's hung, it doesn't shake with the earth. So the paper is actually shaking and the pin staying the same. If you've ever been in an earthquake, sometimes you'll see like the chandeliers will shake, and it's like that same kind of concept. Really, the chandelier is staying still while the house is moving because the ground is what's shaking. And so this is what that printout would look like. So here's an earthquake. And so we have those primary waves that hit first, and then here's the secondary or the shear waves that come in a little bit later. And they travel at different velocities through different types of rocks. And knowing that you got to know the rock type, and you can calculate then how far away the earthquake that focus was. So if this was 8 minutes, you can do some math and figure out how far away from this seismograph that earthquake occurred. Let's see. So the density of rock will affect the travel time. The more dense the rock, the faster the waves will move through it. And the seismograph records different waves function. Okay, so yeah, requires 3 seismographs to locate an earthquake. So here's a picture of that. This is just a simple triangulation where if you have seismographs here, and then doing that math of the difference between the P wave and the S wave arrivals, then you know, okay, well, the earthquake from this seismograph was at this distance, and this seismograph was at this distance, and so forth. And then where those 3 intersect is where you have the epicenter and the focus. Now, it is a little bit more complicated than that because of the different travel times and different rock types and densities. So it's a quite complicated calculation you're doing, but this is the principle behind it. And it's a very simple principle behind it. So if all rocks were homogeneous, meaning the same, then this is what it would be. Earthquake energy is, again, just the energy released during the earthquake. It's stored as it's bending, and then it breaks, and all that energy is released as things snap back together, and you feel that shaking. So the magnitude is the amount of ground motion related to that, and the intensity is how much that affects humans and our structures. Different ways of measuring the magnitude. The first and probably the most famous way, even though this isn't really how earthquakes are reported anymore, is the Richter scale. It's logarithmic, so you have 10 times more magnitude or earth shaking between a 3 and a 4. Now, however, the amount of earth shaking isn't the same as the amount of energy released. So between a 3 and a 4, you only have a difference of a 30 times or greater, not only 30 times different of energy released as compared to the 10 times difference in the amount of earth shaking or magnitude. Now, however, the Richter scale was developed in California because there were a lot of earthquakes in California, so they were probably studying earthquakes there before the rest of the country. But that's really only relatable then to strike slip faults, and it's newer rock out in California, and the newer rock isn't as brittle as the older rock in the rest of the country. And the older rock is going to react differently than the newer rock in California. So now what we usually report is this moment magnitude, and it takes into account more aspects of the earthquake. So not just the amount of ground shaking, although it does, but it also takes into account the displacement along the fault and the strength of the rock. So if you have a very strong rock that's broken versus a very weak rock, obviously you have more energy going into breaking the strong rock. And the moment magnitude takes all of that into consideration, where the Richter scale does not. And so here's this example that in Chile, this earthquake had a Richter scale magnitude of 8.9, but on the moment magnitude, it was 9.5. So it was actually a larger earthquake than the Richter scale would have reported it as. And so just again, so right here is all of the parameters that go into the moment magnitude. So the area of breakage on the fault, the amount of displacement along the fault, and then the strength of the rock. Here is just a chart showing the frequency of the different size of earthquakes. So you get about 1, 8 or greater earthquake a year. But then you get up to, like 13,000, 4 to 5 earthquakes a year. Earthquake intensity is how we feel it. So is it damaging our structures, our highways, are people hurt during the earthquake? So this takes into account the amount of energy and the rock type, but as well as a lot of it is location. Obviously, if something happens like under New York or LA, it's going to have a lot more damage associated with it than if something happens in like South Dakota. And we report those as ranging from 1 to 12. And so here is what those look like. And so how bad is it? If it's felt indoors, it's a 3. If your automobiles are affected, it's an 8. Although we don't really use this. If the USGS is reporting a scale for an earthquake, it's going to be that moment magnitude. And here's just an example from this 1886 earthquake in Charleston of the different Mercalli intensities. And so you can see as you get away from that epicenter, it does get lower and lower in intensity, with some exceptions based on rock type or structures. More structures, maybe weak structures that fall down more easily. Maybe they aren't built to an earthquake code. All of those kind of things can go into this Mercalli intensity. And that is it for seismic waves.